Hello, welcome to Understanding Power Electronics. A boost converter has two modes of operation, continuous conduction mode and discontinuous conduction mode. The performance of the converter is quite different between these two modes of operation. In this video, we will understand how the operation of the boost converter is under DCM or discontinuous conduction mode. So that's our aim. Let's get started. We will see now how the boost converter operates under DCM. We assume that the converter is ideal, the switch and the diode and all other components are ideal, and also that the circuit is operating under steady state. These are the two assumptions that we are making in doing this analysis. This kind of analysis is known as DC steady state analysis. We will understand the operation of the converter using a few waveforms. Here, Ts is the period of the switching, T on is the on interval of the switch, and T off is the off interval of the switch. T on by Ts ratio is the duty cycle D. As T on is varied between 0 and Ts, the duty cycle will vary between 0 and 1. T on is D times Ts, duty cycle times the period, and T off is 1 minus D times Ts. We will plot four waveforms: Vs, the switch voltage, Vl, the inductor voltage, IL, the inductor current, and ID, the diode current. These waveforms will help us understand the DCM operation. First, we will go through the operation of the converter step by step. We are assuming that the operation is already under steady state. The output voltage has reached its DC value, so V0 has certain value. We are assuming that C is large, so that the ripple in the output voltage is neglected. This is the common point of the circuit. We will take that as 0 volts. When the switch is on, the voltage on the anode side of the diode will be 0, and the voltage on the cathode side of the diode will be V0, which is a positive value, so the diode is reverse biased. So the circuit splits into two parts. So there is a current flowing on the input side from the source via the inductor and the switch. There is another current flowing from the output capacitor to the load. The output voltage is sustained by the capacitor. We are of course assuming that the capacitor is so large that as it discharges into the load, the voltage does not change much. So during the T on interval, when the switch is on, the switch voltage will be 0, and the inductor voltage will be Vin minus the switch voltage, that will be Vin. And that Vin is applied across the inductor, so the inductor current will go up. The inductor current starts from 0. A little while later, we will show how it starts from 0. Since the diode is switched off, the diode current ID is 0. Inductor equation is VL is L dIL by dt. So dIL by dt is VL by L. VL here is a constant voltage Vin. So we have a constant slope of the inductor current Vin by L. With that slope and that duration, the current reaches a peak of IP. Now we switch off the switch. As we switch off the switch, the inductor current is interrupted. The inductor current will start to fall. As it falls, a negative voltage will be induced in the inductor, this side being positive and this side being negative. The induced voltage in the inductor and the source voltage will add together, and that will forward bias the diode to make the inductor current flow to the output side. So when the switch is switched off, the inductor current continues to flow to the output side via the diode. The waveforms during this interval will be as shown. The switch is switched off, the diode is conducting. We are assuming an ideal diode, so the diode voltage is 0. So the switch voltage will be the same as the output voltage V0. This side of the inductor is now V0. This side of the inductor is Vin. So the inductor voltage will be Vin minus V0. Since V0 is positive and higher than Vin minus V0 will actually be a negative quantity. Now, this Vin minus V0 is applied across the inductor. So the inductor current falls at the rate of Vin minus V0 by L. In discontinuous conduction mode, the energy in the inductor at the end of the T-on interval is insufficient to keep the current going through the diode to the output side throughout the T-off interval. The current falls at such a rate that it hits zero before the end of the cycle, before the end of the T-off interval. During this interval, the diode current will be following the inductor current. So the diode current will have the wave shape as shown. Starts from IP and goes to zero as the inductor current goes to zero. This is the interval when current goes to the output. That is the energy transfer interval. That is the interval when the electrical power goes to the output side. Please note that this is not the free wheel interval. There is no free wheel action here. When the diode is conducting, the source is connected. So we can call this as the current fall interval TF. Once the diode current hits zero, it cannot go negative. So the diode switches off. Let's continue the waveforms under this condition. We'll plot the waveforms and then we'll go through the waveforms one by one. The switch is not conducting, the diode is not conducting, so the diode current is zero and the inductor current is zero. Since the inductor current is zero, dIL by dt is zero, so the voltage VL is zero. And when the voltage VL is zero, if you look at this loop, Vs, the switch voltage, will be Vin minus VL. VL is zero, so that will be Vin. This interval is the discontinuous interval. This is the interval when the inductor current is said to be discontinuous. Neither the switch nor the diode is conducting in this interval. Notice that T-off interval is split into two sub-intervals TF and TD. So TF plus TD equals T-off. So this is one cycle of operation. The inductor current has returned to zero at the end of the cycle, so the next cycle it will start from zero. The inductor current starts from zero and returns to zero before the end of the cycle. Now this process continues. This is again T on, Vs switch voltage is 0, VL is Vin, and the slope of the inductor current is Vin by L, and the diode is off, so the diode current is 0. And then this is the TF interval. During the TF interval, the diode is conducting. Since the diode is conducting, the switch voltage will be V0 and the inductor voltage will be Vin minus V0, and the rate of fall of diode current will be Vin minus V0 by L. The diode current and the inductor current will fall to zero by the end of the TF interval. Again, the next interval is TD interval, when neither the switch or the diode conducts and the switch voltage is Vin, the inductor voltage is 0 and the inductor current is 0 and the diode current is 0. During the TD interval, the only part of the circuit that is alive is the output side. Capacitor is taking care of the load. No current is flowing in any other part of the circuit. This is the average of the switch voltage, Vs average. We'll find out what the average of the switch voltage is. If you look at this loop, Vin minus VL minus Vs is 0. Vin is a DC quantity, VL and Vs vary with time. VL and Vs are periodic waveforms. They have average values and fundamental and harmonics. Kirchhoff's voltage law will be applicable to each one of these components. So we can apply the Kirchhoff's voltage law to the average values. That is Vn minus VL average minus Vs average equal to 0. And VL average is the DC voltage across the inductor. There cannot be any DC voltage across the inductor under steady state operation. If VL average is not 0, that means cycle by cycle the average current will be changing. That means we are not under steady state. So VL average is 0. So what it means is Vs average is Vin. So the average of the switch voltage is the same as the input voltage. That is what we have noted here. We also noticed that during the TD interval, the switch voltage is Vin. So Vs average line will be coinciding with the Vs waveform during the TD interval, ideally. In the boost converter, the inductor is connected to the source. So the inductor current and the input current are the same. In equals IL. So IL average will be the input DC current. The capital I indicates that it is the DC value here. The diode current flows into the output side. The DC part of the diode current cannot flow into the capacitor. Again, if it flows into the capacitor average voltage will be going up or down. That means the converter is not under steady state as we assumed. So the average of the diode current is the output DC current. The ripple in the diode current flows into the capacitor and is absorbed by the capacitor. Next, we will look at the inductor voltage waveform. The integral of the inductor voltage waveform over a period must be 0. That is called volt-second balance. Simply put, it means that the area under the curve inductor voltage in AC steady state in any circuit should be 0. There is a video on inductor volt-seconds balance in this series of videos. You may want to go through that video. So A plus plus A minus equals 0. We can compare this with how the inductor voltage waveform looks like under continuous connection mode. The inductor voltage waveform under continuous connection mode looks like this. Here, in one cycle of operation, you have two intervals. When the switch is on, the switch is conducting, diode is off. When the switch is off, diode is conducting for the whole of the off interval. The inductor has sufficient energy to keep the current going to the output side throughout the off interval. Here also volt-second balance is valid. So that means A plus plus A minus must be 0 here also. Notice that A plus is the same in both the cases. A plus is V in times T on. A plus is the area of the rectangle. Here also it is V in times T on. So A plus is the same. Here A minus is V in minus V naught times T off. In discontinuous conduction mode, A minus is V in minus V naught times TF. And TF is less than T off. Think about it carefully. What that means is the magnitude of V in minus V naught must be more in discontinuous conduction mode compared to the CCM operation, or the V naught should be larger. In the case of continuous conduction mode, by applying volt-seconds balance, we can get V naught equals V in by 1 minus D. DCM, V naught will be more than V in by 1 minus D. It has to be more in order to achieve the volt-second balance. We saw how the boost converter operates under DCM. Now we will see the relationship of the DCM operation to CCM operation and the boundary operation. We will see two waveforms, the inductor current waveform and the diode current waveform. That is IL and ID. This shows the inductor current waveform under continuous conduction mode, ILC, C standing for the continuous conduction operation. During T on interval, the current starts from I1 and goes up at a slope of V in by L. And when the switch is switched off, the current goes through the output diode and the current falls at the rate of V in minus VO by L. Here it is indicated as V in minus VOC by L. VOC standing for the output voltage under this CCM operation. The current at the end of the T-off interval returns to the original value I1. Because the operation is in CCM, the inductor current stays above zero. When the switch is off, the inductor current flows through the diode. So this part of the inductor current forms the diode current, IDC, C again standing for CCM operation. The average of the diode current is the output DC current. I have marked that as IOC, C again standing for CCM. The corresponding input DC current under CCM is I in C. It is the average of the inductor current. Now in CCM, V0 by Vin is 1 by 1 minus D. Assuming ideal operation of the converter, no power loss, the converter has 100% efficiency, then V0 times I0 equals Vin times In, or V0 by Vin equals 1 by 1 minus D equals In by I0. So In by I0 ratio is a constant value 1 by 1 minus D for a given duty cycle. Now if we reduce I0, as we reduce the load current, the input DC current will also go down proportionately. So as the input DC current goes down, the inductor waveform also will go down. At some point, the converter will operate at the CCM DCM boundary. The inductor current under that condition is shown here. That is the orange curve ILB. Here, during the T-on interval, the current starts from 0, goes up at the same slope Vin by L because Vin has not changed. And after the T-on duration, the current reaches a peak of IP. After it reaches the peak, when the switch is switched off, the current flows through the output diode. The current comes down at a slope of Vin minus V0 by L and reaches 0 just at the end of the T-off interval. And the current starts to rise again. Notice that I have marked the downward slope as Vin minus VOC by L. VOC because the output voltage is going to be the same both under boundary condition and under CCM operation. Again, this part of the inductor waveform forms the output diode current. I have plotted it here, IDB. During the T-off interval, the diode current starts from IP and then follows the inductor current and goes to 0 at the end of the T-off interval. The average of the IDB waveform is IOB, which is less than IOC. The corresponding input current is I in B, which is the average of the inductor current ILB. I in B by IOB ratio will still be 1 by 1 minus D. Now we adjust the load such that it draws even less current. When that happens, we go into discontinuous conduction mode of operation. We just now saw the waveforms under DCM operation. Let's reproduce them here. This shows the ILD waveform, inductor current waveform under DCM. Notice that during the T-on interval, ILD waveform and ILB waveform are identical. The currents start from 0, the slopes are Vin by L, and the currents reach a peak of IP. This part of the inductor current ILD is the diode current as before. The inductor current ILD comes to 0 before the end of the T-off interval. That interval is the current fall interval TF. And this interval, when the diode current is 0 and the switch is also off, is the TD discontinuous interval as we saw before. The average of the diode current is the output DC current IOD, which is less than IOB, which is less than IOC. Likewise, the average of the inductor current ILD is I in D, which is less than I in B, which is less than I in C. The area of the orange triangle AB divided by the period TS is IOB, the boundary output current. The area of the green triangle AD divided by the same period is IOD, the output current under DCM condition. Just intuitively speaking, the heights of the triangle is the same, IP. So the average current is reduced by reducing the base of the triangle. The base of the current is reduced means the diode current comes to zero earlier than the T-off interval. And that is facilitated by the output voltage going higher and the slope and the downward slope V in minus V naught by L increasing. As the load current is reduced, the area of this triangle AD will become smaller. The inductor current's downward slope will be steeper. Output voltage will be higher. There are a few videos in this series which you may find useful. One is PE2B1 boost DC-DC converters CCM operation, which discusses the CCM operation of the boost DC-DC converter in detail. Second is PE2B2 boost converter, the boundary between CCM and DCM. This video discusses the boundary operation between continuous conduction mode and discontinuous conduction mode of a boost converter. And the third video you might find useful is PE2A4, which is on buck converter, understanding DCM operation. This video, if you go through, you will be able to appreciate the differences and commonalities between DCM operation of a boost converter and a buck converter. Next, we will derive an equation for the output voltage V0. The method that I'm going to introduce here is a relatively simple method. It's, I believe, easy to understand. So let's do that. We will use some of the waveforms that we saw earlier. This is the VL waveform, swings between Vin and Vin minus V0, and in the TD interval, it remains 0. This is the inductor current, goes up at a slope of Vin by L and comes down at a slope of Vin minus V0 by L. During the TD interval, it remains 0. This part of the inductor current during the T-on interval flows through the switch, and this part of the inductor current during the TF interval flows through the diode. So we can draw the switch current and the diode current separately. This is the switch current, starts from 0, goes to IP at the end of the T-on interval, comes down to 0 and stays at 0 till the switch is switched on again. This is the ID current, diode current, stays at 0 except during the TF interval, current fall interval. During this interval, the current starts from IP and goes down to 0 in the diode. The average of the inductor current, as we saw, is the input DC current. IL average is IN. The average of the diode current is the output DC current. So ID average is I0. The average of the switch current is the DC switch current. It's nothing special. In this derivation, we will start with finding the average switch current or the DC switch current. Why? Because we can do it. That's why. If you look at the switch current, it's easy to plot. We know everything about it. We know that the current starts from 0. We know that the slope is V in by L. We know V in. We know the inductance value. Let's say the design is given to you. So we know the slope. We know the T-on interval, the duration for which the switch is on. So this waveform is clearly known to us. So we can compute the average current directly. So that's where we will start. IS average is IS, the DC switch current. That will be equal to 1 over Ts integral 0 to Ts IS dt. And integral 0 to Ts IS dt is this area AS. So the average switch current is AS by TS. AS is simply the area of this triangle, which is half IP times T on. And T on is DTS. So TS and TS will cancel and we will get IPD by 2. So the average DC current is the peak current of that waveform times the duty cycle divided by 2. We can find the peak current in a straightforward manner. Peak current is the slope of the inductor current times the T on. So V in by L times T on will be equal to IP because the current starts from 0. So IP is V in by L times DTS. T on is DTS. So we can substitute this IP here. IS, the DC switch current, will be V in by L times DTS times D by 2, and that will be V in TS by 2L D squared. That is equation number 1. We assume we know the input voltage, the switching frequency, the inductance value, and the duty cycle, and we can determine the DC switch current. We are continuing the derivation. Now we have the switch current, but switch current is an in-between current. It's neither the output current nor the input current. So we have to relate the switch current to the input current and the output current. Let's do that. We look at this node A. First, let us write the KCL, Kirchhoff's current law, for the instantaneous currents at node A. So IL equals IS plus ID. Notice the lowercase I to indicate instantaneous values. Now, these are periodic waveforms at a period of Ts. So IL average will be equal to IS average plus ID average. You know that the IL average equals IN, the DC input current. IS average is IS, the DC switch current. And ID average is the output current. So IN equals IS plus I naught. IS, we have already derived an equation. I naught is the load current. We assume that it has been specified. So in this equation, only IN is not known. Step 3 is we apply input-output power balance. That is V in IN, the DC input voltage times the DC input current equals V naught I naught, which is the DC output voltage times the DC output current. We assume 100% efficiency. There is no power loss inside the converter. So V in IN equals V naught I naught. We can substitute for IN from here. V in IN will be V in IS plus V in I naught, and that is equal to V naught I naught. So I can find V naught by V in. So I just have to take the V in to the right hand side and I naught to the left hand side. I will get V naught by V in equals IS by I naught plus 1. We have already derived an equation for IS. We assume that I naught has been given to us. So all we need to do is plug in the expression for IS and we'll be done. Notice this equation. This equation is in an interesting form. It is 1 plus something. So we know that the minimum gain will be 1. So when the switch current is 0, that means the switch is always off. Duty cycle is 0. The gain is going to be 1. Otherwise, the gain will be 1 plus IS by I naught ratio. The switch DC current divided by I naught, that will be the additional gain over 1. Step 4 is obvious. Just substitute for the switch current. So we have two equations. The first equation we got was for the switch current, V in Ts by 2L d square. The second equation is for the gain, V naught by V in is IS by I naught plus 1. We just have to take this IS and substitute it here. So then voltage gain or the voltage ratio of the boost converter under DCM will be V naught by V in equals V in Ts by 2L d square by I naught plus 1. That's it. We are done. As you can see, this is a simple and concept-based derivation. This is the equation we just now derived. V naught by V in equals V in Ts by 2L d square by I naught plus 1. Notice that V naught by V in depends on duty cycle as you would expect, but it also depends on output current, and also it depends on the input voltage, the switching frequency, that is Ts, period, and the inductance value. In the CCM case, V naught by V in is simply equal to 1 by 1 minus D. It was not dependent on the load current. It was also not dependent on the switching frequency, inductance, etc. Now we will do a simple check on the derived equation. The check is like this. Let's say this is the CCM region, this is the DCM region, and this is the boundary. The CCM voltage gain equation is valid at the boundary. The DCM voltage gain equation is also valid at the boundary. So we will take the DCM voltage gain equation and then apply the boundary current expression. So I naught, we will set it equal to I naught B. So at the CCM DCM boundary, I naught B is V in Ts by 2L d times 1 minus D. So there is a video in this series 2B-2 in which the boost converter's boundary operation is explained in greater detail. This equation is derived there. You may want to refer to it if you are not familiar with this. So we take this I naught B and substitute for I naught in this equation. So V naught by V in will be V in Ts by 2L d square divided by I naught B plus 1, and I naught B is V in Ts by 2L d times 1 minus D. V in Ts by 2L, V in Ts by 2L will cancel. So D and one of the D in the d square will cancel. So we will get D by 1 minus D plus 1. And if you simplify this, you will get 1 by 1 minus D. So we have shown that at the boundary, this equation simplifies to the CCM equation. We have come to the end of this video. In case you like this video and this series of videos, please click on the like button and subscribe to this channel. You may also wish to share this video with others who may find it interesting and useful. Thank you.